So let's continue on the silicon qubit, right? Last time we talked about how to do initialization and also do the readout, spin to charge conversion. Today we will continue, but before we continue, I just want to do some Zeeman splitting calculation, right? This is a hint, okay? You know you're going to have midterm, so pay attention. So, you know you can have one cheat sheet, right? Two-sided. Okay, you can bring it to here, so it's closed book, but you can have one cheat sheet. Now, so let's review what silicon qubit is about, right? It's under an external magnetic field. In this case, I'm going to use 1.4 Tesla, and under the temperature 50 millikelvin, right? Last time I had typo, this should be T2, and this is T2 star. We know that when you put it under the magnetic field, there will be a splitting in the energy, right? Remember? If it happened that the magnetic field is pointing down, this time I use pointing down, right? So do you get higher energy or lower energy when you have a spin that is pointing down? So when your spin pointing down, then what happened to the magnetic moment? It's up. So when it is pointing up, then you have this Hamiltonian, which is negative mu dot B, right? So if it is pointing up, and this is pointing down, then this is negative, different direction, whole thing is positive, right? So if it is pointing down, what did I ask you? Spin pointing down, right? Then you have higher energy, right? The one pointing up, you have lower energy. Is that okay? Yeah. So, but how about the change of the difference in the energy? As we said before, this is like they call it Zeeman splitting or Zeeman energy. Right here, I call it ground state. Ground state is pointing up. Total energy is 2 mu B0, okay, which is equal to h bar omega L, the Larmor precession frequency. Is this clear? Any questions? Let's do some calculation of this system, the nature paper I showed you in the last class. But actually, I make some modification, okay? So I say the magnetic field instead of, wow, I put 10 Tesla. I hope that my cheat sheet is correct. Okay, magnetic field is at 10 Tesla, very large. I think this is just for the sake of calculation, but I don't know why I put 10. And then the temperature equals to 10 millikelvin. Okay, so what is the splitting of the energy? We just said that. What is that? Remember the equation? 2 mu B, right? Of course, everything is in its absolute value. Okay, now mu we can approximate by, not approximate, we can just directly use the gamma times the spin, right? Gamma times the spin give me the magnetic moment. Do you remember? Because magnetic moment is equal to the gyromagnetic ratio times the spin, right? Do you still remember this? You forgot put in your cheat sheet, right? And what is gamma? Gamma, in this case, it is G divided by 2, right? So I decided to just put the absolute value here. And the spin is easy. Of course, h bar divided by 2, right? Sorry, gamma is not just G divided by 2. What else? M. E over M, thank you, right? And you make sure you put this in your cheat sheet and other tips. Then this is what? What is this? Times h bar divided by 2 and then times 10. Is this okay? How I substitute it? Make sense? Right? So with this, then I'm going to do substitution. I keep the G because I want to discuss the value of G later. Two got cancelled. Electron charge 1.6 times 10 to the power negative 19. The mass of electron, it is the rest mass. We are using rest mass here. So it is 9.1 times 10 to the power negative 31 kilogram. right? And then h bar is what? 6.626 times 10 to the power negative 34. I actually remember I did not know a cheat sheet, right? Divided by 2 pi. And divided by 2, right? Because h bar is h divided by 2 pi, right? And then the whole thing times 2. Yeah, question?
So the mass is effective mass, or there's a difference?
Here I use the rest in electron mass. For here, I put everything into G. Okay, so in the paper they also do that. So they have a very special value of G. Okay, but the reason is that sometimes people just use this whole thing. I think it's this one, as the Bohr magneton. The Bohr magneton is using the rest mass of the electron. Okay, and then we just lump everything into G. Right, so it depends on your situation. So you can play with the effective mass and the G together. So in this particular case, I use this M, right? You can decide what to do. Okay? How do I find the rest mass?
Rest mass.
The mass of the electron, the rest. Rest, R-E-S-T, not moving. Because when it is moving, due to relativity, your energy actually is much higher. Yeah, because whenever they talk about moving electron, it's all about this high energy particle collision, right? Collision. So we call it rest mass. And you know what? It seems that I'm Bohr magneton. Oh, I know what's going on. I might have some problem here in my number because I see my cheat sheet doesn't have this 2. I forgot about the whole thing. No, G. Oh, the whole thing times 2. No wonder. Thank you. So this one got no. That one no. This one is got cancelled by this one. 2 times 2. 2 divided by 2, yeah. So I still have a 2 here, right? So I think I missed something. Maybe you go back to redo the calculation to make sure what it is. But anyway, my calculation is that when G equal to negative 2, then I get energy equal 1.159 millieV. Okay? Now, what is the meaning of millieV? What is EV? What energy in terms of EV? Do you know? EV is the energy gained by one electron charge when you travel across 1 volt. Okay, so millieV is actually an energy unit. So in order to get the unit in joule, you need to do this one divided by 1.6 times. Not divided, it should be times, right? Multiply by 1.6 times 10 to the power negative 19 millijoule. Okay, but we always use the millieV. Okay, so if you plug in this equation, you get this. So how about let me show. This connection is so bad.
The millieV, that's equal to the delta E, is that correct?
Is equal to delta E, correct. Okay, I'm worried about this recording. Let me stop it. So it doesn't hurt. Actually, let's just do I always say my class is like a tutorial, right? I really want you to get everything in the class instead of going back. Of course, you're supposed to go back to study. Let's just to plug in the number. 1.6 times 10 to the power negative 19, right? Divided by 9.1 divided by 10 to the power negative 31. Do you see that what I'm doing here? I plug in this. Multiply 6.624 times 10 to the power negative 34 divided by 2 divided by 3.14 divided by 2 and then times 10, okay? Now, if my G is 2, I multiply the whole thing by 2, right? Then you will get this joule. This is the energy in joule, okay? And what is in terms of VV? You will do this one. So I say the wrong thing again. It should be divided 1.6 divided by 10 to the power negative 19. I should divide it, right? So by Q. Then I get 115. Okay, so I keep confusing you. Oh, that is right. That is right because I'm convert to joule, not convert to EV, right? This is joule, right? So do you see what I'm doing?
So the answer is in joules. If you divide by the electron charge, you got the electron.
Correct, right? And that's why I got 1.159 milli EV. Okay, my cheat sheet I just missing this 2, but if I put in 2, I get the right number. Okay. Is it okay? Because all we are doing here is so-called SI unit, right? You use kg, Coulomb, Tesla for all of this. So your SI unit should give you energy in joule, right? So, and then I just jump a step. I actually should get this number. I should get the number on the right. And then I divide the number on the right by 1.6 times 10 to the power negative 19. Then I get the in terms of EV. I think everyone should know how to convert joule to EV. Is this okay? Okay, good. Now, so you see that the separation is pretty large, 0.1 EV, milli EV, okay? Now, let's consider what is the KT. KT or KT over Q, right? Which is the thermal energy. Okay, the average energy of the thermal gas, right? If you try to plug in, I don't have the number, you just Google, you will find that it is the micro EV range? And again, I don't know why this is not consistent in my cheat sheet. So what you need to plug in is the Boltzmann coefficient. Anyone remember what is the Boltzmann coefficient? Say again. Say louder. Oh, 0.026 in terms of EV. No, I don't need to do that. I don't need to go to Boltzmann number. So what I'm trying to do is I can use this. I know it's 25 milli EV at room temperature, right? So I can divide this by 300 Kelvin and then scale it accordingly by how much? 10 millikelvin, for example. This will give me the energy, right? Do you see what I mean? Because room temperature is 25 milli EV, right? Like what it says, 0.026, maybe 26 milli EV, 0.25 point something, right? So what is this number? Right, so it will bring me to, of course, minute divided. So this one can be confusing. Also, I should not put Kelvin. Then otherwise, you think it is K. All of them are Kelvin, right? Millikelvin divided by 100 Kelvin, right? So this one from this to here, I go 1,000 times smaller, becomes 25 micro EV, and then divided by 3, right? So it is like 25 micro EV divided by 3, which is about 8 point something, right? 8.3 maybe micro EV. Is this okay? Right, so basically you see that I am able to separate the electron, separates the energy of spin up and spin down way much higher than the thermal energy, right? In this case, it's almost 100 times higher, which is good because if you put your you put your qubit, let's say at higher temperature, for example, room temperature, The thermal energy is way larger than difference between of the two level already. You cannot do any processing, right? Because the coherence time is going to super short, and you cannot distinguish whether it's spin up or spin down. Make sense? Okay. Now, however, in the paper, okay, in the reference of that paper, reference 18 in that paper, right? So I did not put the name. I think it is this one, right? Because this is a follow-up of the last lecture slide, and we were talking about another paper. But anyway, for the reference of that paper, what it say is that they found that G is equal to 0.4. Okay, 5 times smaller than -2. Okay, 5 times smaller. So if that is the case, then it means your delta E is equal to 230 micro EV. So why does this happen? I really don't know, because the system is very complicated. It changed the gyromagnetic ratio. You may say that, is it because the effective mass change? But usually, right, this one I forgot if gallium arsenide or silicon, but it won't be way larger than 1, right? Effective mass of silicon is what, 0.2 in the longitudinal direction, 0.8 in the transverse direction. If a gallium arsenide is even lighter, or maybe, I don't know which value, but it won't be 5 times heavier, right? Because if you want to get this number lower, you need to have an effective mass 5 times heavier, right? But experimentally, they got G equal to -0.4, right? So that is just the overall effect, which they did not explain, and I don't know why, but just a complicated system. What we have learned about this spin is all about on vacuum. But now you are actually an electron in a solid state material, a crystal, right? So there are many things happening, okay? But so this just want to bring the perspective to you, right? Now, if you read this paper, you understand what happened. And I see many papers, they just say assume G, just effective G equal to something, because that is not something they want to study. They're more like an engineering paper, okay? Okay, good. So we are done with this. Any questions?
I haven't seen that happen, so I haven't seen, but they show like a magnetic field versus frequency to show the slope of the line, which usually is used to calculate that G. So that's how they.
They might have, but I think that paper did not use that to find the G. They just deduce G from the Larmor frequency. So basically, they get this delta E, and then they deduce back what the G is.
For just one particular, because usually these diameters are taken very big, and they see how the Larmor frequency, then that's a linear relationship, and using that slope, they can calculate.
That's what I remember, but you can take a look, right? I did not recall they did that, but maybe they put in the supplementary material. You know, in Nature they have the main paper.